Okay, welcome to this session. Yes, in the previous session we have seen takeaway game and discussed the optimal play of players. We also introduced the formal definition of combinatorial games. So, to recall, in a combinatorial game there are two players. A combinatorial game, there are two players make moves alternatively. This is the first point. The second point is that there are finite set of possible moves. Then we also have to specify the rules specifying these rules specify how players make what are the possibilities a player has from a given position, or given once a player makes a move, the next player where he can lead to. All that the rules are specified. Movements from a position to other positions. So, this is a very important thing, and then we also need to say that the game ends when a player cannot make a move. And then the fifth one is game eventually ends. Okay. So, these 5 rules specify a combinatorial game. These are the definition for a combinatorial game. Now, we need to understand these 5 rules does not say who is winning or anything. So, the winning in general are specified by 2 things. One is called normal play, the other is called measure play. In a normal play, the last player to make a move winners. He is the winner. In measure play, the last player to make a move is loser. So, despite the fact that seemingly they look the negation of the other, but they are different, we will see them later. Okay. So, we also discussed about the positions. So, there is something called N position, the other is called P position. A position in a game, in a combinatorial game, is called N position if the person who is going to make a move from that position, he is going to be the winner, whereas in a P position the person who had made the move, the previous person who made the move, he is going to be the winner. So, these are mainly for win loss games. Here we are not considering the draw option. Of course, it is possible to include the draw option. Now, let us look at a simple game and we will discuss how this can be done. Let us look at the chomp game. I will consider a very simple chomp game. So, this is the poison. Okay. Now, this is the initial position. Now, from here what happens is that there are multiple possibilities that can happen. So, from here it can go to the following thing. This happens if this particular thing is taken by the player. Now, it is also possible that it can go to this position. If this happens, if the player 1 takes this, and of course there is another possibility is this one. Now, from here it leads to only one this thing, this is the terminal position, and from here again it goes to this, and from here it can go to either this or this, and so this is known as a game tree. Of course, even though I have written it like this, putting this one, but we can actually say that the game tree has the following thing. There is a position here, and from here there are several possibilities, and then this gives you another position of the game, and from here again go and like this goes, and finally there will be terminal positions, and in this terminal position it may be, it will say whether player 1 is winner. So let us say, let me put it as a +1 -1 or -1 +1 or 0 0 -1 +1. What I mean to say that here the player 1 or the left player or the blue player is winner. In this case blue player is winner. Now in this case red player is winner. And in this case it is a draw. So this game tree is a very powerful idea. In fact, we will explore this game tree in a later course, later part of the course. So right now we will present a very important result where we use this idea of game tree. So in fact, if we recall, we have not said anything about the following fact. Given a game, how do we know that a person can win or not? So is this possible, is it really possible that the person, one of the player will always win? So that result is actually given by what is known as a very famous result due to Zermelo. So we will use this, we will discuss this Zermelo's theorem, which actually tells that in any game of whatever we have been discussing, either the first player has a winning strategy or the second player has a winning strategy or there is a draw. So what it says is that in any game with WLD, so player 1 has a winning strategy. Or player 2 has a winning strategy, or the game ends in a draw. So in any game, one of the three holds. Okay. So in any combinatorial game with, we are taking this win, loss or draw, all three possibilities are there. In such games only one of these three will hold, either one holds or two or three. So this result is a very bold result, and Zermelo's actually has discussed this problem in connection with chess. Okay. So let us, the chess is a quite an interesting game in the sense that of course it looks like that chess is a finite game, but is it really finite game? See, for example, in chess you can actually repeat certain moves, and if you repeat certain moves, then what happens is that the chess is not going to be a finitely terminating game. So in order to make it finite, people imposes rules, like for example if you repeat the position thrice, the game ends in a draw. With those restrictions, the chess becomes a finitely terminating game. And then the Zermelo's theorem tells you that in chess either white player has a winning strategy or black player has a winning strategy or the game ends in a draw. So that is the consequence of the Zermelo theorem. So let us try to prove this Zermelo's theorem. How we will prove this? The proof of Zermelo theorem. So the proof is based on induction. Yesterday we have already seen the induction. So once again we apply this induction and we prove it, this Zermelo's theorem. How we go about the proof? So in the induction step, first it is based on the depth of the game tree. So what I mean by depth of the game tree, suppose you take this so if this is the starting position, now here there are 3 possibilities and then from here there are 2 possibilities and then it ends to this terminal node. These are known as the terminal nodes. From here again these are the moves and it goes, and so here these nodes are terminal nodes. These are the terminal nodes. Terminal nodes is where it is whether it is a win, loss or draw, that is decided. Let us go back to the previous thing. So in this game let us rewrite this game once again here in the simple chomp game to see it. So let us look at this chomp game. So one choice, as I said, is it will be like this. The other choice is this. Now from here it comes to so now this is the terminal position, this is the terminal position, this is a terminal position. Now let us look at it. If this is the first choices are by blue, and after this red makes the decision and here again blue made the decision. So let us look at it in this case. So here it is a blue is the winner and here it is the red winner and here again the red winner. Okay. So let us look at it. The blue has taken this one and therefore it has come, and red has taken one of this one and therefore it has come, and blue is the last person to take a move, and then red is forced to take the poisonous chocolate, and hence the blue person is winner. Remember, we are looking at a normal play here. Okay, here. So these are the terminal nodes. Okay. Okay. So now going back to this. So as I said, we are going to use this depth of this game tree. Depth is basically what it means is that, so for example in this game the depth is here 1, 2, 3, 4, basically this entire length of this. Okay. There are 3 steps it is going down. So we are looking at this thing, and if when there is a 0 depth means means we are at terminal nodes. Okay. So, depth is 1 means one position above terminal. So, like this we have the definition of depth. Now, once the depth is there, so we will use this induction. Induction is basically we use induction, depth is basically is what we use, and first thing is that we need to show to prove the induction, to use the induction we need to first we need to prove this. If depth is 0, it automatically means the win or loss or draw is already determined. Therefore, if the depth is 0 means it is already determined. Now, what we do is that induction hypothesis we assume that the result, the theorem is true for all game trees with depth less than n. If the depth is less than n, we are assuming that the theorem holds true. Then in the next step we need to prove the theorem for game trees with depth equals to n. So, let us look at it. It becomes very easy to see the proof. So, now the depth is n. So, that means let us assume the position is here. Now, from here let us assume whoever the player, there are certain choices that he is making. How many it is, whatever it is, there will be some certain thing here, and again here something, here again something, here again something, here something. Let me call this as T1, T2, T3, T4, whatever Tk. So, what here k is basically the number of moves available from this position. Now, look at this. Each of these subtrees T1, T2, this Tk have depth less than n. That is the interesting part here. So, because already this position and from there they made a move, and from this position we know that the depth is n, but already we made a move. So, therefore, the depth has to be less than n. Okay. So, that each of what essentially, let me write it here, each T1 Tk have depth less than n. Therefore, by induction hypothesis viewing this T1 Tk as games on their own, one of the three holds. So, what do we mean by one of the three? Let us go back to the statement. Either player 1 has a winning strategy or player 2 has a winning strategy or game ends in a draw. One of these 3 holds. So that means it is possible that T1 may be a win of some player or draw, like that T2 same, like this Tk the same thing happens. So whatever it is, what it says is that in T1 we know that let us say one of the player is winning or T2 is there. So now what the player at this position can see is that he will look at in T1 he is winner or not or draw, which is the best possibility. Again in T2 is he winning or not, who is winning. See, remember let us say if this position here, let us say in these things, let us say blue has made the move. That means if I say that T1, the game tree T1 is a winning game, if let us say if T1 is, let us say T1 is winning position for player 1 implies, so this position let me call this as a star. Star is winning position for player 2. So it is quite obvious to see this fact, because remember one point which I would like to stress here is that in all these games it is not important who the player is. The important point is who the player who is making the move, who is not making the move, the player to make a move. So if T1 is a winning position for player 1 means what? The person who is going to make a move at the position T1, he is the winner. If the person who is making the move at T1 is going to winner, in fact if you recall that the notation n, this T1 is called n, T1 is n position. So if T1 is n position, star is going to be p position. Okay. So therefore T1 is a winning position for player 1, that is T1 is an n position, star is going to be a p position. Of course there is a small thing, I do not want to use this n position and p positions here, this is just to illustrate this idea only I have used, but because there is a draw here, when n and p positions we are using it, the draw is not taken care here. So we will not use this n and p positions further in this proof, but this is just to illustrate. Okay, if T1 is a winning position for player 1, star is going to be winning position for player 2. So in other sense, by that induction hypothesis we know this T1 can be replaced by, let us say player 2 winning position, maybe T1 could be for player 2 winner, here it could be player 1, here it could be draw, whatever it is. Now this blue player who is making the decision at this place, so he is going to be decide which of these choices are giving him the best. So there are finitely many choices here, there are finitely many choices, and which one of them he is going to choose. Therefore if all of them are losing positions, if T1 is a losing position for player 1, T2 is also losing position for player 2, T3 is also losing position for player 2, all of them are losing positions, then there is no, it becomes a, this blue player is going to be the loser here, and whatever it is he will choose one of them. So in essence what we are really saying is that the induction hypothesis says that with depth is equals to n implies the 3 points. Let me recall. One is player 1 has winning strategy. Second is player 2 has winning strategy. Third is draw, game ends in draw. So, one of these 3 holds for the T1, T2, Tk, and hence for depth is equals to n. Theorem holds for depth is equals to n. This now induction completes the proof of the theorem. Okay. So, to summarize this theorem, what we have really used is just a very simple mathematical principle of induction. What we have said is that if the depth is 0, then obviously the winners are winning, either it is a winning position or a losing position or draw for the players, that is determined automatically. If the depth is less than n, we are assuming that the theorem is true, and then we are showing that if the depth is equals to n, then also one of these 3 holds. So, that proof is very simple, and which we have gone through this one. Okay. So, this theorem actually has introduced us the very crucial point in sense. So, like yesterday we have used this takeaway game, there it was a little easier. So, how we can say whether a game has a winner or not. So, we can use this theorem to say that in any combinatorial game with win, loss, draw, one of these 3 always will hold. Okay. So, that is the essence of this theorem. We keep using this theorem again and again in this combinatorial theory part as well as in the other parts of this course. Okay. So, we end this session with this, and we will continue it in the next session.